So today we'll be hearing from our Associate Director for Science here at the CFA and SAO Senior Astrophysicist, I'm sure you all know, Randall Smith. So Randall received his Bachelor in Science in Mathematics and Physics from Carnegie Mellon University. He then went to the University of Wisconsin-Madison, where he worked with the Space Physics Group and his advisor, Dr. Don Cox. He received his PhD in 1997 with his thesis titled Modeling Soft X-ray Background with Multiple Supernovae. He's involved with multiple X-ray observatories, and he tries to maintain a broad perspective regarding science priorities and astrophysics and their impact on mission requirements and capabilities. His research focuses on processes in the interstellar medium, and on maintaining the atomic database AtomVB that is used throughout the field to model the spectrum of hot collisional plasmas. And today he'll be talking to us about his baby Arcus. So with that,
and I'm Amy's boss, so there's that too. So I'll be talking about the Arcus probe mission. Now, many of you may have vague recollections of a mission called Arcus that was the Arcus Explorer mission, completely independent. That was a totally different mission long ago in a land far away. No, seriously, that was a mission that did X-ray spectroscopy only. It was an Explorer mission. It was very highly ranked in the last review. And basically NASA came back and said, we liked it very much, but we've decided not to select it for a phase A due to programmatic reasons, which is basically NASA-ese for we're not picking it and we're not telling you why. Not that I'm bitter. But this gave us the opportunity to repose as a probe mission. We've added far UV spectroscopy to the mission, as I'll be describing throughout this talk. And you can find out more on our website here, arcusxray.org. We bought the website way back when, and we're not changing it now. Arcus.org is actually owned by a group that does charity work on gay rights and upland mountain gorillas. I don't know why. I'm not joking. That is, in fact, what the website is, the Arcus charitable group is all about. So, with that said, why spectroscopy? Well, this is a slide I use frequently because spectroscopy is in my blood. And this is volume 1, number 1, page 1 of the APJ. And you can see it's a paper by Michelson on conditions which affect the spectrophotometry photography of the sun. So basically, spectral imaging was the very first paper in the APJ. The Astro 2020 Decadal followed this up, noting that astronomy became astrophysics with this first spectrum, and that they predict in the next decade, spectroscopy will be the dominant discovery tool for astronomy. Of course, the great thing about the Decadal is it's got quotes for everybody, so you can pull what you like, but be that as it may. So we have 3 main science topics here. One is based on cosmic ecosystems, and these are all Decadal 2020 priorities. For those of you who've been selling new missions, pull quotes like this and themes you'll be seeing a lot. So phrases like cosmic ecosystems, unveiling the drivers of galaxy growth, and worlds and sun in context are all chapter headings in the Decadal, so we'll be seeing lots more of them. But the first one there is, how do black holes impact their surroundings? And this is, yeah, certainly. Of course it isn't.
okay, so this is what it looks like on the page.
Trying again. Still not advancing. Stopping. Okay, hold on. How long's the pandemic been going on now? What?
Just click share.
Just click share. Okay. We'll try again.
That looks great.
Okay. Is it gone back a screen now? Okay, now we're working. So the studies of AGN have been long awaited in this field. And when I say long awaited, I mean back in the 2001 decadal, the question was, how do supermassive black holes form and evolve? And we're going to look at this with Constellation X. In 2010, it was, how do black holes grow, radiate, and influence their surroundings? And then in the 2020 decadal, they noted that feedback from supermassive black holes and during galaxy formation and evolution is one of the most dramatic examples of the small scale, the tiny little black hole in the center of a galaxy affecting the entire galaxy and beyond. And they noted, thankfully, and I appreciate whoever actually put this text in there, UV and X-ray radiation was key to understanding this process, which is not hard to understand because it's a highly energetic process, which is inherently going to involve X-ray and UV radiation. So what does that mean? Well, it's just too pretty a picture not to include. But the point that the decadal made was that higher sensitivity and spectral resolution in the optical UV and X-ray of the broad emission and absorption line outflows are needed to understand what's going on here. But basically, there's no way, well, I would have said there's no way to image a black hole, but of course now there is, so long as there's one of two black holes we're talking about. But in order to really see the effects of the outflows going on, you're going to have to use spectroscopy to see the Doppler shifted emission and absorption features in that in these coming out of the black holes. So there's been a huge amount of work on this over many years, but some really amazing photos and cartoons been made recently. So here is a recent one from Gandhi et al. Review showing black hole in the center, and then the scale on gravitational radii out to 10 to the 8. And then I will zoom in. I'll let you know that I spent quite a while trying to convince PowerPoint in order to do an actual zoom for those two and failed miserably. But this is the relevant point that I wanted to make. And you can see here that at the very core, right near the black hole, you get relativistic iron K alpha. That's beyond what the Arcus bandpass is going to be looking at. Arcus is really about soft X-rays and far UV. But as soon as you get past about 10 gravitational radii, you start getting effects that are seen in soft X-rays and far UV. And that carries on all the way out towards the torus. Now, so what does that mean? It means that if you want to trace these clouds here that are being accelerated all throughout the AGN, and these are the clouds that somehow go out and impact the galaxy in which they're formed, it depends on how dense these clouds are and how fast they're moving. Basically, it's a question of what punch do the clouds have. And that depends simply on mass times volume, or sorry, mass times velocity. Well, getting the mass is actually really hard because it turns out that there's a degeneracy between where the cloud is, which we really can't know, and how dense it is in terms of a molecular density. But there are a couple of ways of getting that density. One is that if you have a good enough atomic data and a really good spectrograph and the right lines, you can measure the density of the cloud directly from the spectral lines themselves. That depends on having the right lines, having everything be at the right ionization state or temperature, which you may not have. The other way that you can do it is black holes have the advantage of flickering all the time. They go up and down in flux by factors of 2 on a regular basis. So if you are a cloud sitting near a black hole being accelerated, and the cloud suddenly changes its flux to either double or halve, for example, then suddenly all of your ions are going to ionize up or recombine down, depending on whether or not you just got hit with extra ionization or the light just turned off. Either way, that change is going to happen over time. And if you've got a high enough spectral resolution detector with enough sensitivity, you can watch that process happen, and it is density dependent itself. So how fast that process occurs, how fast the recombination occurs, depends on the density of the electrons in the plasma. The more electrons, the faster it'll recombine, the faster it will reach equilibrium at the new ionization radiation fluxes coming in. So Arcus has that sensitivity. So we don't have to rely on just having a cloud that happens to be at just the right ionization state to give us just the right lines to measure a density. We can do it for practically anything, so long as the black hole is flickering. And fortunately, most black holes do that on a fairly regular time scale. That gives us the ability to measure the gas ionization parameter chi, and then pull out the density from the time variation, ultimately giving us how much power is going into these clouds and how much power is going into, thus, the galaxy and shaping things. What does this look like? And this is one of those cheating comparisons that people promoting new missions always show. This is comparing Arcus in 10 kiloseconds on a bright AGN to XMM RGS for also a similar 10 kiloseconds. And here you see the advantage of having a resolution of greater than 3000, where Arcus sits, versus a resolution of more like 200 to 300, which is what the XMM RGS has. Now, the important thing here is not that we're better than XMM RGS. If we weren't, we wouldn't be proposing the mission. The important thing is, this is one of the brighter X-ray AGN that we'd be looking at, and we're going to have a sample of 100 plus AGNs that'll all have data at this kind of quality. So that means we're going to have a sample, it'll have a central peak at around 0.3 Eddington, 30% Eddington luminosity, but it'll range from 0.03, so down at a very low accreting system, up to 2, covering all of those with equal quality data. So finally going from having, instead of just having good data on a few sources that happen to be bright and nearby, we're going to have great data on a whole range, a statistically valid sample of AGN, looking at them simultaneously in X-rays and UV. Again, something that's extremely hard to do today. I mean, obviously we have UV spectrometers on orbit, Hubble, COS, and STIS, and we have X-ray gratings on orbit, both on Chandra and on XMM Newton. But getting them simultaneously to observe the same source is extremely difficult. At the very least, Hubble is in a low Earth orbit, Chandra is in a high Earth orbit. Getting simultaneous observations with both is a huge pain. You can, if you're wondering about that, ask any one of the schedulers in the room for the Chandra mission about how difficult it is to coordinate observations. It is simply hard. With Arcus, both detectors, both spectroscopies, both spectrometers are going to be on the same mission. Everything will be done simultaneously. And what does that mean? It means that, for example, we'll be able to get spectral data like the top one here, which has shown the oxygen 6 line, and you can see all the different components that can be identified, and they can be connected to oxygen 7 components and carbon 5 components. So you can actually line up the different components and see where are we seeing a warm absorber that has, say, both UV and X-ray components. Where is it purely X-ray? Where is it purely UV? How are they varying simultaneously? Because you'll get time variability as well. So this connection here will allow us to really understand how the warm absorbers are moving all the way from the innermost regions of the AGN all the way out to the torus and beyond. Now, I mentioned getting the line diagnostics, and so I just wanted to show one quick example of that. This is perhaps the simplest one, the helium-like system, oxygen 7. And here you have a density diagnostic that works in the following ways. Essentially, you have a forbidden line, the resonance line, and the intercombination line. And the forbidden line will, at high enough densities, not decay via a radiative transition, but actually via a collisional transition. So if the density gets high enough, you start quenching the forbidden line because the collisions will depopulate it rather than radiative transitions. As a side note, there's actually also a 2-photon transition that depopulates the forbidden line transition. And I remember years ago finding that out and asking Alex Delgado about it. And asking him, because there have been detailed calculations that he and others had done of the 2-photon transition from the forbidden line. and asking why they'd been done. Because obviously there was also a forbidden line transition, a radiative transition. And he said that, well, back when those calculations were done, nobody had bothered to calculate what I believe it's the magnetic quadrupole moment was that actually gave you a radiative transition for the forbidden line. So they thought there wasn't a radiative transition at all, and therefore the only way it could decay was via 2-photon. So people did a lot of work, calculated the 2-photon decay, and then somebody figured out that actually there was a magnetic, actually I think it's a magnetic dipole transition that gets you down to there. And that's a much faster transition to actually give you that decay. So interesting factoid about atomic physics. We'll now move on. Anyway, the difference here is you can see that big gray box is the accuracy with which you can measure this transition, this ratio, with the XMM RGS. And then the small orangish box, what you can do with Arcus with I believe in this case, I think 60 kiloseconds is what this one is. The relevance here is look at that gray box here and compare it down here. That covers almost 2 orders of magnitude in density. So if you're trying to figure out, for example, how much punch a cloud has and you don't know its density to within 2 orders of magnitude, you're really going to be suffering in knowing what the force is going to be. Whereas if with Arcus, you can get it down to a factor of say 2 or 3. And now you're at least cooking with gas in terms of understanding what impact that cloud will have on the surrounding medium. Let's move on to another area, topic area. And once again, I've got pull quotes from the decadals. In fact, all 3 decadals, the 3 most recent ones. Now we're talking about the hot halos of galaxies, also known as the WIM problem or the missing baryon problems. It's basically the question that where did all the baryons go? Because if you count up the baryons inside of galaxies, you end up with a much smaller number than you do if, for example, you calculate the same for damp Lyman alpha systems at very high redshift. So we know that these baryons exist. We know that they were out there somewhere in the universe back at higher redshifts. But if we look at nearby galaxies and we simply count up the masses, count up the baryons that we see, many of them are missing. It looks like either they never fell into galaxies or they did fall in and then they got expelled somehow. But we don't know which and we don't know when. So the goal here is to find those baryons. And this is not really just an accounting problem. It's not like somebody stole our baryons and we're going looking for them. The real question is, how did they get there? How do they end up outside of the gravitationally bound structures like clusters and galaxies that we see today? And again, you can see here, because I imagine you've been reading as I've been talking, but the key missing link here is to measure the properties of the diffuse gas between the galaxies. And the key observational probes here are emission and absorption line spectroscopy of the diffuse gas. Now, I will note that SAO has very cleverly covered both aspects of this, because there's a whole 3.5-day seminar next week on LEM, which is focused on, amongst other things, the emission from that diffuse gas at the outskirts of halo galaxies. Arcus is really focused on the absorption line spectroscopy using background light sources in order to look at it as well. Personally, I'd love to have both missions, so we have both the emission and the absorption at the highest resolution we can manage, but I will note that CFA has covered both, both angles on this. So here is a simulation showing why this is important. So this is from the Illustris simulation. On the left-hand side, you see a simulation of structure formation just using adiabatic forces. So no special models here of star formation, feedback, anything special going on. On the right-hand side, you see a model that has included cooling, star formation, and AGN outflows. And you can see the difference here. And you might say, well, sure, if you only include adiabatic basic hydrodynamics, you don't get much. And if you include all these other effects, then you get the gas going all over the place. That's not really a major result. We know that, for example, the left-hand side is incorrect. The right-hand side has got to be what's going on. But the point is, we don't know how this is going on. This includes cooling functions, it includes star formation, it includes AGN outflows. but it's a particular incorporation of that. It's a model of all of those effects, none of which can be known for certain. And the one thing that we do know from numerical models is that if you don't have any data to pin them down, there's usually a whole lot of flexibility in what they end up looking like, depending on how you choose to implement them. So what Arcus's goal is to give some inputs in order to show, pin down what these outskirts really do look like. So this is just to give you a visual of what this might look like. This is a "you are here" figure where we're there in the middle on the outskirts of the Milky Way, looking through the Milky Way's hot halo. And remember, every line of sight to an AGN is going to include an amazing set of data on our own Milky Way halo. So one of the things that's going to be absolutely true here is that just like a Chandra image, for example, contains an amazing amount of data about things that the observer may not have to plan to look for, because the target is maybe in the center of the image, but you've got all those other things in the outskirts. With Arcus, you're going to have a spectrum that might have the feature that you're looking for, say a distant absorbing galaxy, but it's also going to have the local ISM, the local Milky Way hot halo, possibly the local hot bridge connecting us to M31, and other things beyond that. So the amount of extra data that it's going to occur when you have a spectrum from 10 angstroms to 30 to 50 angstroms with a resolution of 3000 or above is immense. So you'll be able to get the mass, temperature, chemical abundances, and the velocity of any, say, the rotating halo of our galaxy. You'll also get the same for the local bridge. And you'll get this again, not only in the X-rays, but you'll also get oxygen-6 and even the Lyman beta lines. Lyman alpha is going to be contaminated by local geocoronal Lyman alpha, unfortunately. Although for slightly shifted systems, you will get Lyman alpha. So we'll get not only the metal lines, but we'll also get the hydrogen lines, so we'll be able to normalize things. Same for helium. What is that going to give us? This is a traditional figure shown in this field, which in all honesty is massively confusing if you're not familiar with looking at it. I'll walk us through it briefly here. On the x-axis is the equivalent width, basically the column density of what the ion that you're looking at here. And this is oxygens 6, 7, and 8. So this is a column density of oxygen 6 of 10 to the 13.4, moderately dense. So out here is going through, say, the core of a galaxy or a fairly dense system. In here, you're talking about going through the outskirts of a galaxy or a lower density system. And these points here, this one and this one, are two detections that exist for what the outskirts of halo galaxy absorption lines look like. And those might look like they're very large error bars, and they are. Those are also incredibly heroic observations to have done. Those took almost a month of observing time with XMM Newton and Chandra in order to get those limits. And the problem here is simply that XMM and Chandra don't have the effective area, don't have the sensitivity to really do this problem the way that we want to. So with Arcus, you'll be able to make hundreds of measurements. You'll be able to nail these curves down far better. This is the oxygen 6 curve. And again, this is one particular model. There's a whole range of models. It's not quite as bad as the famous neutron star equation of state figures where you see the entire lines covering everything from every theorist in the world. But there are still a whole range of models depending on which numerical simulation you use, which covers far more than the range of models that are shown here. So, and the top line there is the oxygen 6 data. And there you can see that actually in oxygen 6, things are pretty good. I mean, that's the model, and those are the data from Fuse. Except Arcus is going to have 10 times the sensitivity of Fuse, which means we're going to get a lot more detections. We're going to be able to drive the curves down from an equivalent width of, say, 10 milliangstroms to more like 3. So we're going to really model this curve extremely well and see if it turns over, see if it turns up, see how this goes. The question of how do the oxygen 6 and the oxygen 7 gas match each other is a really interesting one. because you can imagine that that the oxygen 6 is a transition ion. Does it exist, say, on the outskirts of a bubble of hotter gas that got blown out of the galaxy? So is there a bubble of hot gas that has oxygen 7 and 8 in it, surrounded by a thin shell of oxygen 6? Is it all intermixed because it doesn't collide very often at all? It's extremely low density out there. Keep in mind, the outskirts here we're talking about have densities of particles per cubic meter. So the question of what ionization state this gas is in and how does the oxygen 6 track the oxygen 7 is one of great interest. So pushing on, now we move on to stars. And this is the high energy talk. And as Nancy Brickhouse is fond of reminding me, X-ray astronomers don't necessarily care too much about stars. However, the rest of the astronomy world does find them to be somewhat interesting, not the least of which because there are planets going around them. And if you haven't been paying attention, almost half the observatory is now focused on those planets, which happen to have stars around them. So it behooves people who are interested in high energy to think about the stars that they're going around. And the Decadal felt exactly the same way. They talked about worlds and suns in context. Basically, what the stars do to the exoplanets they're hosting, what's going on here, and noted that UV and X-ray radiation from low-mass stars dramatically alters the chemistry of planetary atmospheres. So there is a new mission being planned. It was called LUVOIR. For a little while, it was called something like, OUVOIR or something like that. It was a really awful name. And then the Committee on NASA Acronyms got together, that's the CNA, and they now renamed it the Habitable Worlds Observatory, HWO, which is also difficult to say. The committee needs to be reformed. But they have a target list of stars that they want to look at. These are nearby stars that may host exoplanets, and they would love to know, for example, what the UV and X-ray radiation is around these stars. One of the things that Arcus plans to do is to do a survey of a number of these stars, perhaps not every star that HWO wants to observe, but we'll be able to get high quality data over a series of years of how these stars are behaving. Are they flaring? Are they bright? Do they have cycles? Many questions that are simply not known, and certainly not at the resolution that we're talking about doing this with Arcus. So we'll talk about also stars that are in formation. And one of the things that we know is that when stars are forming, there's an accretion wind that comes onto the star, an accretion wind that comes in. It then generates a stellar wind that blows things out. The complicating matters is you've got the stellar photosphere and the corona itself, and coronal loops here, that are all competing with each other to generate X-ray and UV light. One of the advantages of looking at a star like this with high resolution data is that you can separate just by the velocity shift, the Doppler shift, the incoming accreting material, the outgoing stellar wind. You can measure both the net inflow onto the star itself in the X-ray, where all the matter is flowing into these forming stars. And you can get their density again by using the same trick that we used with the AGN, again, using the forbidden line, which gets quenched at higher densities. Again, we're going to be doing a survey of stars. So here is a collection of, I believe there's 70 plus stars on this list. And then we'll be adding a bunch more from the Habitable Worlds Observatory. These cover a range of scales. These are the coronal stars, F, G, K, and down to M. And I'll note just in passing, one long-standing question in stars that we hope to at least get some information about, which is that we know how the stellar coronal form, I'm sure you've all heard of the corona problem. Basically, how does the hot corona of a star form? And the answer, everybody knows, small children know, that it's formed by magnetic fields. And if you stop there, all is well. But there are a number of solar astronomers in the crowd, and if you ask them exactly how does the magnetic field do that, then things start to go awry. Because there are models that work very well for the sun. You can apply those models to other stars, they stop working so well. The models require that there be a changeover between the convective envelope and the core of the star, and that that basically you need to have a zone in between these two parts of the star in order to torque the magnetic field lines. The problem is that M dwarfs are fully convective all the way through. There's no layer in between. And yet, if you look at the flux, the luminosity, as you cross that boundary, there doesn't seem to be any signature whatsoever of what's going on. So what's happening? Is it the same process that's going on? I mean, if suddenly when it went fully convective, stars didn't have a corona anymore, this would make perfect sense, but they do. So where do they come from? Pushing on. Now, one thing that's very different from what the Arcus Explorer was, and now the Arcus probe, is that we have added the ability to do transient sources. This might not sound like it's a big deal. After all, you've got the satellite up there in orbit. All we're talking about doing is, instead of having a pre-programmed 5-year mission where we've set all the targets up in advance, we're now putting in the ability to change that target list on a dime. If somebody calls up and says, hey, there's something really worth looking at, please turn the satellite and look at it within 4 hours. That might not sound like it's a huge change to the satellite, and I will admit to you that it is not. It is a huge change to the ground system and the people on the ground. And if you'd like to know more about that, I direct you to some of the Chandra folks that are in the audience who do this for a living, and have cell phones on right now that will beep if something interesting goes off in the sky. So a lot of work to do that, but you can do huge amounts of science this way. So for example, we can look at supernovae. Now, in this case, we're not talking about looking at the supernovae just for their own sake, to see the X-rays and the far UV from the supernovae, but rather a type 2 supernovae is basically a giant light source that lights up the circumstellar medium that got ejected from that star over the past 20 to 50 years. And so if you're interested, and there are a number of interesting questions here about the life cycle of stars and what happens to a star in the last, say, 50 years of its life, a great way to study that is to have a shock wave go across all that circumstellar material, sweeping it up, lighting it up, and observing it in the far UV and X-rays. There's already a fair amount of work being done in this, mostly in the optical and the UV. This will be adding the X-ray and the far UV to that category. Again, you can look at stellar flares and their impact on exoplanet atmospheres, gamma ray bursts themselves. So if you're looking to study the background light from in the halos of galaxies, you can also use gamma ray bursts as backlights. I'd love to say here that we'll also be able to be sensitive to actually seeing features in the gamma ray burst spectrum itself. This has been looked for many times. Nobody's really ever seen anything in the UV or in X-rays in general, but we're going to be much more sensitive. Maybe we'll see something. There's a whole range of galactic sources: novae, black hole outbursts, X-ray bursting, type 1 and type 2 bursts. That is going to be left for the general observer case. So there's a lot of science to be done by Arcus. The baseline science case enables the transient, the TOO detections, but it doesn't use them all up. So a lot of this is going to be left for the general users. Gravitational wave sources. We'll also be looking at TDEs, changing quasars. You can look at solar system planets, again, look at the solar wind charge exchange and so on. So a huge range of targets. And again, the decadal had words to say on this, noting a suite of small and medium scale ground and space-based observatories across the electromagnetic spectrum. So this would be it's certainly at least in the medium scale, if not large, but it's not a flagship. In order to characterize this, we desperately need to have telescopes in orbit that can look in all the band passes that otherwise we will miss, because we know that, for example, gravitational wave outbursts are coming, LSST and Rubin is coming. So we're going to be knowing a lot more about transient sources and what they can do. Now, I will do one last general science topic. And by the way, this is what happens when you start leading missions. Even though your own personal interest is in things like interstellar dust, you can't actually convince anybody to spend $1 billion to study interstellar dust. But it's really sort of interesting because I talked about the missing baryons. There's also missing oxygen. We don't know where some of the missing metals are. And if you measure the total amount of oxygen in the galaxy, it seems like there's quite a bit that can't be found. Now, is the question, is it in gas? Is it in ice on grains? Is it combined within the grain itself? Another question is, for example, is there metallic iron inside the grains or living separately? This is important because metallic iron acts as small little antennae. And if you're trying to measure, for example, the cosmic microwave background or the SZ effect, then knowing how much metallic iron is out there potentially interfering with your sources is a big question. The amount of uncertainty in how much metallic iron is out there ranges from something like 2% of the available iron up to something like 20 or 30% of the available iron. Arcus is going to be exquisitely sensitive to this because the X-rays pass all the way through the grains. And so unlike optical, infrared, or even UV light, which bounces off the surface of the grains, here we're looking through the grains and we'll be able to detect all these features and tell the difference not only between where measuring the total amount of a given element like oxygen, we'll be able to tell in what form it's living. Is it in an olivine or some other, iron oxide form? All of these, Arcus will be able to tell because they lead to small shifts that we can measure in the laboratories. So, continuing on. So, what is Arcus explicitly? By the way, this is one of those fundamental problems with giving a talk like this. Do you start with what the science is going to be, or do you start with what the instrument actually looks like? I decided to start with the science, but so now I'll actually talk about what the capabilities of the instrument are. The X-ray spectrometer goes from 10 to 50 angstrom bandpass. So that covers much of the iron L shell, some of the neon lines, and then the carbon, nitrogen, and oxygen lines from the hydrogen and the helium-like systems, as well down to L shell lines of sulfur, silicon, and so on. The average effective area across that bandpass will be greater than 300 square centimeters, which, yes, admittedly is only about yay big, but compare that to the Chandra HETG area at oxygen 7 of less than 10 centimeters squared. Now, a huge amount of great science has been done with 10 square centimeters of oxygen area at oxygen 7. So I'm not dissing Chandra in any way here. I'm just noting that if you increase that by a factor of 30, you're going to get a lot more science. The far UV spectrometer goes from 1020 to 1560 angstroms, and the far UV cognoscenti amongst you will recognize that as basically going from oxygen 6 through carbon 4 lines and many others in between, with a resolution of that's the requirement is 17,000. The actual expected best estimate is 21,000. That's roughly comparable to what Fuse got. It is a little bit better than what you can get in most observations with costs. The sensitivity, however, is going to be 10 times that of Fuse at oxygen 6. So it's going to be, and this has been an interesting cultural difference between, I'll note here, between X-ray astronomers and UV astronomers. To begin with, X-ray astronomers think in terms of effective areas, UV astronomers think in terms of sensitivities and signal to noise. Never the two shall meet. But more importantly, also, X-ray astronomers think in terms of observations of 50 and 100 kiloseconds, and UV astronomers think more in terms of orbits and more like 5 or 10 kiloseconds. So when we said our baseline observation might be around 100 kiloseconds, they were sort of floored. They'd never seen data that good. So this is roughly equivalent to almost a 19th magnitude in the UV flux. But the key number to remember is that it is 10 times that of Fuse at oxygen 6. All observations are going to be simultaneous and co-aligned. We'll have TOOs with a 4-hour response time. That includes waking the PI up, and a 7-day lunar resident orbit that's similar to TESS. Now, of course, not actual size, not available in stores. Product may vary. This is still the early phases of this mission. Just to give you an idea of what this looks like and why we decided to do this, I'm not going to talk too much about the science or the technology here, but in the front, you have two new technologies. Both involve using silicon in clever ways. The first is the silicon pore optics. Now, these have been developed by ESA over the last 30 years now, and they are robotically built X-ray mirrors. They don't have a PSF or an imaging capability that is close to Chandra's. They're more like 10 arc seconds, not 1 arc second. But nonetheless, they can be made very cheaply, at least as X-ray optics go, and in bulk. So you can buy them from a company called Cosine that makes them for ESA, and they will simply ship them to you. We are actually using the exact designs designed for Athena, which saves us a huge amount of telescope or of design money. Behind those, we have CAT gratings, critical angle transmission gratings. These have been developed over the last 20 years by the team at MIT that also was responsible for the high energy transmission gratings. They are higher resolution than the HTG gratings. Instead of having a resolution of around 1,000 or so, these will in the Arcus system get you to about 3,800. And the MIT folks who make them would want me to say that actually these gratings could get you to 10,000. It's just that you have to put them onto an actual physical real telescope and everything blurs them out. But they're really amazing gratings. They have a efficiency of almost 40%. That can be compared to the efficiency of the HTG gratings of around 2 to 3%. So that's where the improvement is coming from, is you have a lot more area at lower cost from the grating, from the mirrors, and you have a lot more efficiency in the diffraction from the fact that the gratings themselves are much more efficient than they used to be. The detectors here are CCD detectors similar to those on the Suzaku mission. They also come from the MIT Lincoln Labs group that was responsible for building the CCDs on Chandra that were part of ACES. These have been tested. So on the left-hand side here, you see an image of the silicon pore optic image without a grating in front of it. And the PSF that I talked about, the part that's not so great is the long part here that goes this way. That is about a 10 arc second PSF or a little bit better. But the narrow part is intrinsic to the way that the PSF is made, and that's actually less than an arc second in width. We take advantage of the fact that these silicon pore optics are inherently asymmetric like this, and we choose to diffract along this axis as opposed to that axis. And that gives you a much higher resolution. So it's as though we're diffracting a 1 arc second mirror, not a 10 arc second mirror. On the right-hand side here, you see the input source here from an aluminum K alpha line. This is a doublet, and we're looking at it here in 18th order. Actually, the broadening that you're seeing here is not intrinsically from the grating itself. It's actually because the atomic physics of this aluminum K alpha line is such that it has a naturally broad line width, which those of you who are instrumentalists might be saying, why did you choose such a broad line? Why didn't you use a narrow line? And the answer is that basically there aren't in nature any good bright fluorescent lines that are narrow. It'd be lovely if there were, but there aren't. You could get a special emitter that would give you a mono energetic line, but those are very expensive, and Panther doesn't have one that's very bright. So instead we have one that's fairly broad here, and you end up with a line here that gives you the ability to measure the resolution of the detectors. I will note here that the minimum resolution that this system shows is 3,850, but that's the minimum. The uncertainty here is not in the measurement. The uncertainty is that we don't actually know the actual line width of the aluminum K alpha to the accuracy known in order to know it any better than that. Just a little pitch here for Lab Astro, which is another one of my favorite things to do. Now, one of the other things that I will note here is that in order to separate the front half from the back half of the X-ray spectrometer, you need a boom. And one of the problems that many missions had was that none of the TIMCO, the technical reviewers, the engineers who looked at these proposals, ever believed that you could make a boom this big that would be sturdy. So for the last proposal that we did, we actually used the money from that NASA gave us to develop the proposal in order to actually buy a boom that would be of the right size. And there it is. It was amazing how well this convinced the reviewers that in fact we could build one of these things to actually just show it to them and show it that it was very sturdy. This boom is actually then rolls up sort of like a camping tent. So if you're familiar with one of those camping tents that sort of pops open with this poles that then spring into shape, that's exactly how this works, except it costs more like $1 million and not 1995. The far UV detector is a high heritage Cassegrain design. And when I say high heritage, Cassegrain designs have been around since the 1700s. Here's a ray trace of what it's going to look like. But the fundamentals here are that it has a 0.8 meter primary diameter instrument. It's coated with lithium fluoride. And then we will put use a microchannel plate developed by Ozzie Sigmund as the detector on the back end. So this is all TRL9 technology. There's really nothing new in this. This instrument is going to be fantastic, but it's not groundbreaking in any of the instrumental designs. It's just designed to do what we need. So there is the team and all the people involved. It's SAO leading it. And I would say CFA, but when you're doing business stuff, telling people you're both CFA and SAO gets confusing. Goddard is involved. Ames Research Center in California is handling mission management, mission ops. And we have the UV telescope is coming from our friends at LASP in Colorado. So with that, I will finish and take questions. Thank you very much.
Just a comment that I wanted to mention that the Arcus telescope observes the far UV sun and ranges go out here. Range, and so you know, a whole database of flares, 10 years of solar flares, so if it's useful or interesting to that figure.
That's a very good thing to know. Thanks. I should have known that, but yeah.
So, Randall, very nice talk. Your early slides where you were showing the video, you're going to go back to it.
Yeah.
With the flashes going off, I assume those are supernovae.
Those,
And
yeah, those or supernovae, or I believe those are actually like star forming bursts of star formation in the system, or possibly AGN explosions. That was a giant, yeah.
the question of what's heating the gas was largely understood.
The question of what's heating it, yes. The question of just how much heat and how hard it pushes is still a model dependent. So the models generally agree, but they don't perfectly agree. And the case study that I always remember is that the early days of those models always found that there were many more satellite galaxies, dwarf satellites, than are actually seen. And then once this was pointed out, they essentially tweaked the codes in order to tone down the satellite production, and it went away. Which isn't to say, I mean, it's not like they were doing it wrong in the first place. It just they didn't have the data. You know, they made a prediction, it didn't come true, and so they tweaked it. Here, I think we just don't have the data.
Thank you very much. You may have said this actually, but do both channels, the soft X-ray and the operate simultaneously on the same target?
They do, yes. Yes, so that's one of the key features of this design, is to have both of them at the same time. We will probably have, and I didn't go into too many of the details of the technical side. In order to get on the UV side, we have basically a 600 angstrom bandpass with resolution 20,000. And when you combine those two effects, you can't get all of that into one microchannel plate all at the same time. There's basically too many resolution elements, and we can't design something that's big enough. So the plan is to have a rotating grating that moves back and forth. So you do the short wavelength and then the long wavelength and the short wavelength again at whatever cadence you need. There'll be, with the latest design that we're looking at, there'll also be a third option where you can get lower resolution, perhaps resolution 5,000, and you get the entire bandpass in one go on the detector with somewhat higher sensitivity due to the way that the system is made up. So one of the debates we're having within the team is whether or not people will find higher resolution where you have to basically chop between two modes to get the full spectrum, or lower resolution where you get it all at once, all the time. Feelings are mixed as to which one of those two modes is going to be the more popular with general observers.
Follow-up question, I think. For the test like orbit,
Yes.
do you have down?
Downlinks will be about once a week. And so the plan is we'll have contacts with it via S-band at any time. We can contact it anywhere in the orbit, but the downlinks will be when it comes close to perihelion, and those will take about 4 hours. Igor?
What's the advantage of using microchannel plates rather than the party?
I believe it's a combination of sensitivity and the resolution element size, the pixel size of the microchannel plates. So you'd have to use even more of them.
So what class mission is this and how long would it be?
It's the AO calls for a 5-year mission. They are saying that it is class C. People who are intimately familiar with NASA regulations will note that typically 5-year missions cannot be class C. That point has been raised to various people and they've said, no, don't worry, it's 5 years and still class C. All we can do is go by what they told us.
What limits you to a 4-hour response rather than something much better?
Much better than 4 hours. We've got about a half hour to slew and a half hour to guaranteedly, connect up to the satellite and get it in connection. So that burns an hour right there. And then we're estimating an hour to do the calculations of making sure that we're not pointing at the sun or drifting past the moon or something like that we're not allowed to do. And then 2 hours for basically deciding that we're going to do the entire thing. We're hoping that we can beat 4 hours. And my guess is that we probably will, but we think that we can show that we can do 4 hours without breaking the bank.
So I won't ask about storage one, but how bright can you go before?
I will note that the Stellar team was chatting about looking at Zeta Pup, and the far UV folks, the detector folks, were going, you didn't tell us you wanted to look at Zeta Pup. We will most likely have a neutral density filter to handle bright sources. The problems that, for example, COS has, where they can't look at practically any M dwarfs because they might flare, will not affect us. The newer generation of microchannel plates have much less sensitivity to sudden flaring. So you might get pileup, and so the data during a flare may or may not be as good as you want it to be, but it won't be forbidden because it won't ruin the detector. And if you're looking at something that's truly bright, then we would simply put a neutral density filter in the way. You could also use, just as a side note, just like Fuse was used, there'll be a slit on the far UV detector, so you can also use it to drift over a source and do emission line spectroscopy in the far UV with it as well. The resolution with that mode will be far lower. It'll be more like 1500, not 20,000, but you will be able to get, for example, drift over a starburst galaxy and get emission line spectra around imaged from the entire galaxy.
But on the X-ray side?
Only on the far UV side. The X-ray spectrometer does not use a slit. It's a slitless design. There are some crazy people who've come up with X-ray slit designs for spectrometers, but none of them are practical at the moment.
Going once, twice. All right, well, thank Randall again for that.
Thank you.